Hi, today we will discuss beams, especially the shear and bending moment diagrams. For an overview, uh, we will review the relations of load, shear, and moment, particularly its derivation, the moment discontinuity, and concentrated force, and some examples. Then we will look into the procedure for analysis and more examples for the shear and moment diagrams. As a review, remember if the variations of shear V and moment M as functions of X are plotted, the graphs term the shear diagram and moment diagram uh, name respectively. In cases where a beam is subjected to several concentrated forces, couples and distributed loads, plotting the shear and moment versus X can become quite tedious since several functions must be plotted. Of course, there is a simpler method for constructing these two diagrams as we will discuss here. A method based on differential relations that exist between load, shear, and moment. Here we will consider the free-body diagram for a small segment of the beam having a length, differential length, the delta x. This segment has been chosen at a point x along the beam that is not subjected to a concentrated force or couple. Any results obtained will not apply at points of concentrated loading. The distributed loading has been replaced by a concentrated force, which is equal to W times delta x that acts at the fractional distance epsilon. Of course, the epsilon should be taken from 0 to 1. In this case, the value of epsilon is 1/2 because the concentrated force W delta x is applied at the middle. Then applying the equilibrium equations, we have summation forces y is equal to 0. So look at this diagram on the right. We have the shear V plus W delta x. By the way, the distributed load is positive upward and it should be negative downward. So here we assume that it is upward, so it is positive. Minus the right shear, we have minus V plus delta V, which is equal to 0. So in this case, V will be cancelled out because there is another V on the other side. So the remaining value is the change in shear, which is equal to the weight or the distributed load W times delta x. If we sum up moment at point 2, that is at the neutral axis location, the shear on the left will cause a clockwise bending, that is V times delta x minus this moment minus this concentrated or distributed load W delta x times epsilon delta x. Of course, in our case, that's 1/2 plus the remaining moment m plus delta m, which is equal to 0. Again, some of the terms will be cancelled out, especially the m. So the remaining portion of the equation is delta m is equal to shear delta x plus the uniformly distributed load W epsilon delta x times delta x. So dividing by delta x and taking the limit as delta x approaches to 0, these two equations, this one, the change in V is equal to W delta x and delta m is equal to V delta x plus W epsilon delta x square will become these equations. So the change in shear, that is dV over dx, is simply equal to the uniformly distributed load. Always remember this one. The change of the shear is equal to the intensity of the load. Or in other words, the slope of the shear diagram, because it's the change dV over dx, so it's the slope of the shear diagram is equal to the intensity of the distributed load. remember this equation. The other equation is that the change in the moment dm over dx is simply equal to the shear, or since this is the first derivative of the moment diagram, it is the slope of the moment diagram is equal to the shear. So in other way around, you can say the first equation is the slope of the shear diagram at a point, which is equal to the intensity of the distributed load W at the point. The second equation can be stated as the slope of the moment diagram dm over dx is equal to the intensity of the shear at the point. This equation can also be integrated from one point to another between concentrated forces or couples, in which case it will result to the two equations again. The first equation, the change in shear, is simply equal to the integral of the loading W times dx. This is the change in shear, which is equal to the area under the distributed loading diagram, or it can be stated as the change in the shear between any 2 points on a beam is equal to the area under the distributed loading diagram between the points. So this is very useful equation in drawing the shear diagram. Also, the second equation involves the change in the moment, which is equal to the integral of the shear times dx, or the change in moment is equal to the area under the shear diagram. Or it can be stated this way, that the change in the moment between the 2 points equals the area under the shear diagram between the points. Take note that these equations provide a method for determining the numerical values of the shear and the moments at various points along the beam. But take note, from the derivation, you have to remember that the equations of shear above cannot be used at points where a concentrated force acts, since the equation do not account for the sudden change in shear at this point. Also, because of the discontinuity of moment, the two equations for moment cannot be used at points where a coupled moment is applied. In order to account for these two cases, we must consider the free body diagrams of a differential element of the beam below, which are located at concentrated force and coupled moment. So instead of using the uniformly distributed load here, we apply a concentrated force F and a coupled moment M prime. What will happen? So from the figure, with the concentrated load applied, it is seen that the force equilibrium requires the change in shear to be delta V is equal to F. So the change in shear is simply equal to the distributed load, or the concentrated load F. Thus, when the force F acts upward on the beam, the change in shear is positive. Remember this one. If F is acting upward, then the change in shear is positive. So that the shear diagram shows a jump upward. So you will see later on when you are drawing, it will just jump upward. But if F is acting downward, then the jump will be downward, meaning the change in shear is negative. How about the moment? Using the moment equilibrium requires the change in moment to be the change in m delta m is equal to m prime. So in this case, if an external coupled moment m prime is applied clockwise, then remember the change in moment is positive. So the jump will be upward also. So when m acts counterclockwise, then the jump must be downward, or it is negative. So remember these roles, because these are very important in drawing the shear and moment diagram. To give you some insights on the relationships between loading, shear, and moment, it would be much better if you will see it visually. Here are some of the types that HIBBELER presented in table 4.1 of his book. The first column is about the loading, the second is the shear diagram, and the third one is the moment diagram. So for the first type of beam with the loading P, look at this one. If you have a load P and a shear on the left VL and shear on the right VR and the moment ML on the left and MR on the right. If you draw the shear diagram, or the shear diagram here, is the change in shear is simply equal to the distributed loading W. But since we don't have the distributed W, we only concentrate on the distributed or the concentrated load. So here, there is a change in, or there is a sudden change in load. We have the shear VL, so there will be a jump because this is upward, so it should be positive. So you can see VL jumps upward. And since there is no loading between VL and P, the shear is constant, or the slope is equal to 0. And since P is directed downward, this will jump by P. Okay, and then also since there is no loading between P and VR, again the shear is constant, or slope is 0. And then at the end, the shear is downward or negative, so there will be a downward change of shear equivalent to VR. So with that, we can also see the moment diagram here. We have a jump ML because this is positive. It will jump ML, and then the slope. Remember, the moment diagram is or the change in moment is simply, or the slope of the moment is simply equal to the shear. So here, the slope will be equal to VL because the shear at this portion is equal to VL. Okay, and then at the joint, or at the point of discontinuity, that is at the point of loading of P, the slope will change because the shear here is equal to VR. The slope will be equal to VR, and then there will be a sudden downward moment which is equal to MR. Okay, so as you can see, we are using directly the definition of the change in shear, which is equal to W, and the change in moment is equal to V. How about if we have a couple M prime applied at this portion? So first, there will be no shear in this case, only the moment ML, MR, and M prime. So the slope is 0, and then there is a sudden upward moment ML. This is ML, and since there is no shear here, then the slope is also equal to 0. ML is constant, and then there is a sudden downward uh, value of M prime, with then uh, uh, a 0 slope, and then there is the sudden downward value of MR, which is equal to this one. Also, with the uniformly distributed loading W is above, so we will have the shear VL and moment ML, and so with the other side, the shear VR and the moment MR. In drawing the shear diagram again, it will jump by VL upward, and then uh, the shear will change due to this applied W sub O, which is going down. So since this is going down, the shear will also be decreasing. So here it is decreasing towards the right with the slope of negative W sub O. Remember, if W sub O is going up, that is positive, but if it is going down, it should be negative. So that's why it is negative. So this the line is also going down. Then at the right hand side, there will be sudden change of shear, that is VR, up to 0. So here we have a constant slope which is negative W sub O. And if you draw the moment diagram, we have ML, sudden upward couple ML, and then the slope at this portion is simply equal to VL, or the shear at that particular point. But as it changes position, the value of VL will also, or the value of the shear is also changing. So that's why the slope here is also changing. The value of the shear is decreasing, so this is also decreasing. The slope is also decreasing up to equal to VR. Okay, so then there is a sudden downward MR that is equal to MR. So look at this table. If you have a concentrated load, the shear is will be, or the slopes of the shear should be zero, and then the moment diagram, the slope should be equal to 1. So for the beam with the couple M prime applied, there is no shear, so the slope is 0, and then the moment diagram has also a 0 slope. Of course, there is no shear here, so the slope should be equal to 0. If it is uniformly distributed loading, shear has a slope, a constant slope, and then the moment we have a positive decreasing slope. Of course, it's positive because it's upward, but the value of the shear is decreasing, so that's why the slope is also decreasing. For other types of loading, this is a triangular loading. As you can see, the shear diagram, we have VL, it goes up, and then the slope should be equivalent to the loading at this portion, that is W1. But since the load is increasing, then we have an increasing slope. But of course, since W is going down, so it should be negative increasing slope up to W sub 2 or negative W sub 2 at the right hand side, where the slope is equal to the shear BR. Then we can go directly with the shear VR. And the moment diagram here is equal to a jump of ML, and the slope is equivalent to, at this portion only, is equivalent to the value of the shear VL. And then since we are in the positive portion, and take note at the slope of the shear, which is uh, decreasing value, I mean the value of V here is decreasing, so the slope in the moment diagram should also be decreasing. So we have a positive decreasing slope here, and then at the end we have the MR, so it will go down by MR. And so with this type of loading, this is the directly the opposite of the above loading. So the shear VL, and then the slope is decreasing. Yeah. Again, it's negative decreasing slope, and then we have VR at the right side. And then for the moment diagram, we have ML, it goes up, and then the slope should be equivalent to VL. But take note, the value of the shear here is decreasing, so that we should have a decreasing slope for the moment. And then at the right hand side, we have the slope, which is equivalent to the shear here, VR. Then we have the MR. So in general, as you can see, for a concentrated load, we have a zero slope for the moment, and then 1 degree. We have to increase it by 1 degree for the moment. For a couple, we have a zero slope here with zero slope also for the moment. For a uniformly distributed load, the slope is zero, but for the shear, we will have to add 1 to make 1 degree curve, and this is the second degree curve. For this one, a first degree curve loading, and the shear will be a second degree and a third degree moment. Just add 1 for every case. So here we have again 1 degree slope of the loading. This shear will be +1, so 2 degree curve, and then this is a third degree curve. This always the this trend is the same wherever you go. So for the procedure for analysis, for the support reaction, you need to determine the support reactions and resolve the forces acting on the beam into components which are perpendicular and parallel to the beam's axis. Remember, you have to resolve the forces into components for easier drawing of the shear and moment diagram. And for the shear diagram, you need to establish the shear, that is V and the x-axis. So we have the vertical v-axis and the horizontal as the x-axis, and you have to plot the values of the shear at the two ends of the beam. Since the change in shear is equal to W, the slope of the shear diagram at any point is equal to the intensity of the distributed loading at the point. Note that W is positive when it acts upward. Begin by sketching the slope at the endpoints. If a numerical value of the shear is to be determined at the point, one can find this value either by using the method of sections or by using equation for the tree, which states that the change in shear force, this is the equation that we are talking earlier, the change in shear force is equal to the area under the distributed loading diagram. And since Wx is integrated to obtain Vx, if Wx is a curve of degree n, then Vx will be a curve of degree n plus 1. This is I am talking earlier. You just have to add 1 for the degree of the curve of the corresponding shear. So if you have uniform W, then your Vx will be linear. For the moment diagram, we also have to establish the M and the x-axis, and we have to plot the values of the moment at the ends of the beam. And since the change in the moment is equal to the shear V, the slope of the moment diagram at any point is equal to the intensity of the shear at the point. Begin by sketching the slope at the endpoints. At the point where the shear is 0, the change in moment is equal to 0, and therefore this may be a point of maximum or minimum moment. So this is very important because in design we need to look for the maximum and minimum moment. So look for the 0 shear, and that would be the location of the maximum or minimum moment. If the numerical value of the moment is to be determined at a point, one can find this value either by using the method of sections or the equations that we have stated earlier, that is, the change in the moment is equal to the area under the shear diagram. Since the shear is integrated to obtain the moment, if the shear is a curve of degree n, then the moment will be a curve of degree n plus 1. Again, we will just add 1 for the degree of the curve for the shear to moment. So for example, if your shear is linear, then your moment m will be parabolic. Here is an example, a very simple example, but at least you will see the, the effect on how to draw the shear and moment diagram. We have two horizontal members of the power line uh, support frame, which is subjected to the cable loadings as shown below. So we are required to draw the shear and moment diagrams for each member. So if we have to look only for one of the beam, as you can see, we have named this A, B, C, D, E because there are loading at the endpoints and at the middle. So that's A, B, and E, and the support is located at point B and point D. So if we have a loading of about 4 kilonewton for every wire, 4, then the reaction should be 6 at point B and point D. So this is the complete pre-body diagram of the beam with the reactions. So here we will draw the shear diagram. First, at the endpoints, at x is equal to 0, the shear is equal to -4. Look at this one. The force here is downward, so it should be -4 kilonewton. And at the end, that's x is equal to 6 meters, which is going down. This is positive. Remember this one. On the left hand side, upward as positive, and on the right hand side, downward as positive. Maybe you will be confused right now, but just remember that one. Okay, left upward as positive, right downward as positive. So here you should draw first the shear at the left. Again, you have to draw first the V and the x-axis, and then at the left side you have to draw negative 4 kilonewton. So it should be going down, and at the right hand end, that's positive 4 kilonewton going up because it's positive. So there will be 4 here and then 4 negative 4 here. Okay, so as indicated, the shear between its concentrated force is constant. Remember, there is no concentrated load or uniformly distributed rather load. So therefore, the W is equal to 0, or the change in shear is equal to 0. The shear just to the right of point B here, or the ray, C or D, of course, can be determined by the method of sections. You can just cut at every portion of the segment so that you will be able to determine the shear. Of course, if you have to cut this portion, then the shear is constant from A to B, which is equivalent to -4. If you cut also between the segment BC, then we have the shear 6 minus 4, that's +2, which is also constant. Yeah. And also we have, if we have to cut at CD, the shear should be equal to -4 minus 4 plus 6, that's -2, so it's also a constant. If we have to cut here, we have 6 plus 6, 12 minus 4 minus 4, that's +4, so it's also a constant here, which is +4. So as you can see, starting from point A, the shear goes down, which is -4, and we have a constant shear -4 up to point B. And since there is a sudden change here of loading, that is the 6 kilonewton shear, and it should go upward because this is positive. So -4 plus 6, the shear directly above is equal to 2. And as we have done earlier, the shear here is constant up to point C. At point C, there is this sudden change of load again, the 4 kilonewton concentrated load. So 2 minus 4, because this is negative, then it will cause a -2 shear. Again, this is constant, and then there is a sudden change of loading here, 6. So -2 plus 6, that's 4. And then constant. And since there is 4 here, we have drawn already the shear here, which is +4. And as soon as they intersect, then your shear is correct. Okay, so that's how we do or draw the shear diagram. Then after drawing the shear diagram, we can now draw the moment diagram. Again, the moment, the endpoints at x is equal to 0 should be drawn also, and on the right, x is equal to 0, the moment is 0. There is no moment here actually, so this is 0. And at the same time, at the end point, x is equal to 6 meters, the moment is also 0. Then after plotting those values of the moment, the slope of the moment diagram within its 1.5 meter long region is constant because the shear V is constant, so it should be linear. Take note, the slopes are constant, so your slope should be constant also, or it should be linear. The degree here is 0 and this should be 1 degree. So with the other moment, so as you can see here, or you can just directly use the area between the points A and B, the area of the shear, that is 4 times 1.5, that's equal to 6, but this is negative, so -6. 0 plus -6, so that's why the moment is -6. And also you can add 2 times 1.5, that's 3, so -6 plus 3, that's -3. And then another one, -2 times 1.5, that's -3, so -3 minus 3, that's -6. And we have 4 times 2, that's +6, so -6 plus 6 is equal to 0. Then you can just follow the slopes, because here we have the shear is negative constant, so the slope for the moment should also be negative constant, that's going down. And so with the other side, the shear is positive constant, so the moment here is also positive constant. So that's how easy we draw the shear and the moment diagram. I hope you were able to follow it. We have another example here, a triangular loading. First, we look for the support reactions. Of course, you already know how to compute the reactions, and I will just assume that you can do it by your own by now. So you can use the equations of equilibrium to compute for the reactions. Here, the reaction on the left is 30 kilonewton and on the right 60 kilonewton. So we expect here, because the loading is triangular loading with the, this is a straight line, so the shear, the degree of the curve of the shear should be second degree, and the moment should be +1, the third degree. So here we can draw now the shear diagram. Again, by drawing first the shear at endpoints, we have a shear here 30 kilonewton, which is positive, and then at the end there is also a negative shear, which is -60. Again, on the left hand side going up for the shear is positive, and on the right hand side going down as positive. Since the shear here is going up, so it should be negative. So you can draw first positive 30 on the shear axis, and then at x is equal to the end portion of the beam, the shear is -60. Okay, note that the shear diagram starts with zero slope here. Look at here, W is equal to 0, so it starts at 0 slope, so this is horizontal here. Okay, at x is equal to 0, and it will end at 20 here, so that's -20. So the slope here -60 should be -20. So from 0 to -20, the slope for the shear diagram. Take note, as since the triangular loading goes downward, so your shear will also go down up to -60. Again, we have a negative increasing W, so our shear should be, or the slope of the shear should be negative increasing. Note that the point of zero shear here, as I have said, this is very important because it might tell us the maximum or the minimum moment, and the maximum or minimum moment is very important in the design. So we need to determine the location of this point of zero shear. First, there are many ways to do it. One way is using the method of sections. We have to cut at this portion of the beam for the beam segment of length x, as shown here in the diagram. We will equate that shear equal to 0 at that cutting portion. So as you can see, 30 kilonewton the reaction minus the resultant of the triangular loading, that's 1/2 20 times x over 9 x, then equate to the shear v, which is equal to 0. So you can solve for x here, which is equal to 5.2 meters. Again, I just want to emphasize here, you need to use ratio and proportion to get the height of this triangle. Okay, ratio and proportion for this particular loading. Another way of doing it is just look at the slope. You can just divide it directly with the slope to determine the location of the zero shear. So here, after drawing the shear diagram and determining the location of the zero shear, we expect that at this location the moment is maximum. So again, for the moment diagram, we need to plot first the moments at the left portion and the right portion of the diagram. Here, we don't have any moment, so we simply put 0 on the left and the right portion. For a distance x is equal greater than 0 to 5.2 meters, the value of the shear is positive but decreasing. Ayan. And so the slope of the moment diagram is also positive and decreasing. So you can see here we have W negative increasing, so the shear slope should be negative increasing. But from the shear, we have positive shear which is decreasing, so your slope should be positive decreasing also, but the value should be positive of the moment, but only the slope is decreasing. And here at the right hand portion, the shear is negative increasing. This is negative, but it's increasing, so the slope should also be negative increasing, but the for this one the moment is still positive. So for this distance from 5.2 to 9 meters, the shear and so the slope of the moment diagram are negative increasing. So the maximum value of the moment is located at this portion at zero shear. And how do we determine that value? You can just compute the area of this curve. Take note, we have a first degree curve for the loading, and the shear should be second degree, and the moment should be third degree. I hope you will be able to determine the area of a second degree curve. Do you know how to do it? As long as one of the end is the slope is zero, you can just use 2/3 of the base and the height. 2/3 of 5.2 times 30, that's equivalent to 104. Or another way around, if you are not quite sure, you can just directly sum up moment here at this portion at the distance 5.2. By summing up moment here, we have 30 kilonewton times 5.2 minus the resultant of this triangular loading times the centroid, and it will give you the maximum moment, which is shown here. That's 104 kilonewton meter. So you can just draw directly the moment diagrams here. This is positive decreasing, so your slope is also positive decreasing in the moment. And first degree shear is second degree, and your curve should be third degree. And so with on the other side, it should be the shear here is negative increasing, so your slope of the moment should be negative increasing, and if first degree, second degree, and the third degree curve. So here it shows that you have a positive bending for the whole beam. Also, you can look for these three examples. I will just show you directly the solutions and the values, and I would like you to do it by your own. You try working on this example so that you will feel or you will develop your skills in drawing the shear and the moment diagram. It's very important that you have to develop your skill in drawing this shear and moment diagram because it's very important in structural engineering. So here you can see the shear and the moment from the first degree curve to the second degree and a third degree moment. And so with this one, as you can see, we have a first degree, second degree, and a third degree, but we have a uniformly distributed loading here, zero slope, the 1 degree and a 2 degree curve. And then for this particular one, since there is a discontinuity here at these 3 points, and there is no loading here, so your slope or your shear here is just constant, and then your moment will be a straight line. But for this particular portion, this is uniformly distributed, so zero slope, first degree slope, and a second degree slope of the moment. Also, we have another example. This is a beam used to support a portion of the overhang for the entranceway of the building. And the idealized model for the beam with the load acting on it is shown below. If we have to assume B is a roller here and C is a pin, then we can draw the shear and moment diagram for the beam with the loading of 10 kilonewton per meter. This is quite simple actually, because this is just a simple beam with a simple loading, but it's important that you will however simple the problem is, it's important that you will understand the concept of drawing the shear and the moment diagram so that it would be easier for you to perform the drawing. So here, since there is no shear here, so it's zero, and a negative shear minus 2.9. So you can just draw it. And then we have a uniformly distributed loading, 0 degree curve. Then the next one is the 1 degree curve. Then there is a sudden change of loading here, which is upward, and then going down. So with the bending moment, this is the first degree, so second degree, and then first degree is also second degree. Here, as you can see, we have 4 locations of the 0 shear. Here, the first location, so we expect a minimum or maximum moment. Reaction B, we have 0 shear here, so we expect the maximum or minimum moment. And here, there is another 0 shear, so we expect a minimum or maximum moment here, and so with the support. So as you can see, at those 4 locations, the left and the right, we have 0 moment, so that's not a useful one. But the most useful bending should be at the support for the overhang and at this portion. So we have a minimum value of negative 2.81 and a maximum of 0.239. So that's one of the application of why we draw the shear and the moment diagram, because we want to know where is the location of the maximum shear, maximum moment, because these two is very important in our design. So here the maximum moment is located at support B, so with the maximum moment. So we can design using the maximum shear and the maximum moment at that particular portion. We have a more complicated one. I hope you will not be uh, confused with this one. This is quite challenging for you guys if you are still learning how to draw the shear and moment diagram, because this is a compound beam, assuming that at point A has a roller and at point B we have internal hands, meaning there will be no bending here, and C is taken as a roller and D as a hand support. Of course, if you just follow the formula for determining the determinacy of this one, you will know. You can count mentally. We have two members here, AB and BE, and then the reactions will be 1, 2, 3, 4, 5, 6. 6 plus the number of members, that's 2, so we have 8 compared to 3 times the 3n. So you will notice that this is statically determinate actually. So you just have to separate the two segments. AB, this one, you can compute for the reaction here, and you can compute the corresponding reaction here, and transfer it to this portion. So as you can see here, here is the free body diagram of the reactions, and you can use the equations of equilibrium to compute for the reaction. Again, I will assume that you already know how to compute for the reaction, so I will not repeat it here, but it's very important in our exercises, in our exams. You really need to compute the reactions. You cannot just say, I already know this one, and so this must be the reaction. No. You have to compute and show it that it's the proper or the correct reactions. So as soon as you will do that, you will notice that at the ends it will be useless, because the reactions there, the internal reactions will just cancel out because they are the same but in the opposite direction. So here, as you draw the shear diagram, again, draw first the shear at one end, left end, that's positive 4, so you will draw positive 4, and a positive shear on the right hand side, that's positive 6. Okay, so you can draw that way. After that, since we have a uniformly distributed loading, so the shear should be decreasing. So 4 minus 20 times the length of the beam, that's 10 feet. So 20 times 10, 200. So 4 minus 200. Am I right? 10 feet. Yeah. 2 times 10, so that's 20. So 4 minus 20 is equal to minus 16. Take note, of course, there is no loading between B and the pipe keeps loading, so your shear should be constant. And then there is a sudden change of pipe, so minus 16 minus 5, so that's minus 21. And again, there is no loading here, so your slope or your shear is constant, which is minus 21. And there is a sudden change, so 45 here, the reaction here is 45. So minus 21 plus 45, that's 24. And, and then we have a triangular loading, so that's going down, so your slope should be going down, or your shear should also be decreasing. So the loading is 3 times 1 half times 3 times 12, so that's around 12. So 24, am I right? 1 half times 3, the height, times 12. So 12 divided by 2, that's 6 times 3, that's 18. So we have 24 minus 18, so the result is 6. We just cross the value of 6 at the right support. So here is the shear diagram of the beam. As you can see, from this portion, you will see the slope is decreasing, or the concave downward and then concave upward, because of the type of the loading actually. So as you can see here, it is increasing and then decreasing, so there will be change of curvature. Actually, it's quite common or easier if it is increasing, then your curve will be concave downward. And if it is this is increasing, if this is decreasing, then it is concave upward. So there will be a change in slope here at this portion. Then you can draw the moment diagram. Again, you need to draw first the moment at the left and the right portion of the beam. So at the right there is no moment, so that's 0. And on the left we have 60, so it will go up, that's positive. And take note, this is the zero shear, so the moment here should be positive. Look for this distance. You can use meter of sections and sum up the moment to compute the maximum moment here. That's 64 minus the area of this triangle. 64 minus the area of this will be equal to this value, which is 10. And then 10 minus 16 times this distance, it will give us minus 96. Then minus 96 minus this area, minus 21 times this one, that's 4. So it will give us minus 180. And then minus 180 plus the area of this. This is quite challenging. How you determine the area of this? Again, you can use the 2/3 height times the base, but only at this portion. And then at this portion, not 2/3 but 1/3 already, because the area here is at this portion. And then take the area of the other rectangles. Or else you can also sum up moment here. Check if it is correct or not. And it will give you the correct value of the moment. Okay, so that's all for drawing the shear and moment diagram for beams, and I hope you already learned how to do it. But again, it will really need time to practice, a lot to practice actually, and later on you will realize it would be easier already. As of now, I know it's quite difficult, but with practice, with diligence, and with all these exercises, in no time you will learn how to do it. Okay, so that's all for today, and thank you for listening.